Welcome back to the Team 24 Senior Design Project. This is the drilling machine that we are making for Koops Incorporated. Now let's go over in detail a few of the things that we discussed in the shorter video. We're going to go over the machine process, some of the machine components in greater detail, and some of the machine specifics, the ins and outs and inner workings of how it goes. Let's start with the process. So the way this is going to work is that an operator is going to be wanting to put holes in this aluminum extrusion. What they're going to do is they're going to place the extrusion into the machine, into this slot that we have for it. Over here we have our cycle start button. The operator touches off this optical touch, and these clamps are going to actuate forward and hold the part in place. Next, the operator is going to come over to the human machine interface, the HMI over here. They're going to use the touch screen to enter the part length, where they want the holes. Is it a rectangular profile or a square profile? How many channels that they need drilled? And that's going to determine how the program enacts from that point onward. Once all that data is in, they can start drilling and the machine will take over. Once the drilling is all completed, the clamps will retract and the operator can remove the part and place it into the tap channel. Now, the tapping will not be required for every single part, but for those that it is required, we will have a channel right here with clamps at the end of it. The clamps will secure the part in place, and a manual tap gun, which is not currently installed, will come over here, and the operator will guide the tap gun into the holes and drill the ends of the extrusion to put the threading into it. That will be the whole system. The operator can do the tapping while the machine is drilling the holes, because the hole drilling is entirely automatic and requires no operator input once the cycle has begun. So let's go over a few of the specifics of the machine, starting with the drill station itself. We have these drill clamps right here. They're wide clamps with a very wide face to them so we can get the maximum amount of friction grip. The face is a polyurethane face, which allows the part to be gripped firmly so that it doesn't rock during the drilling process. We can see that we have these different upstops and backstops spaced out between on the work surface here. The reason why they're raised and apart from the walls here is so that chips can fall and gather into this space without landing on the work surface and making it hard for the operator to load parts. Cleaning the surface is going to be easy. The operator can simply take an air gun attached to this air nozzle down here and blast through the work surface, cleaning off all the chips. The backstop here should collect the chips and allow them to fall into these holes here that we specifically designed for chip mitigation. Over here, we have this cylinder placed at the end of the workspace. This is our end stop. There's one at each extreme end of the machine. What's going to happen is the operator is going to zero the part to this cylinder. The cylinder will actuate upward and provide a stoppage space for the extrusion to go no further. There's a part presence sensor back here letting us know that we have an extrusion segment in the machine ready to be drilled. Now, the reason why these stops are on cylinders is so that if we have a piece that's longer than the workspace of the machine, we can still drill it. The stops can retract, allowing the piece to go out via these holes in the side of the machine here. There are thumb screws in the back that the operator can remove to allow this whole panel to come off and allow a longer piece than the machine to exit out the machine, giving us a full 9 feet of drilling space on maybe a 16-foot part. So what would happen with a 16-foot part is that the drilling machine can drill 9 feet of it. The operator can then slide it through, reset the stop cylinder, and the machine can drill the remaining 7 feet without any trouble. So let's talk about the drill. The drill unit we have here is a motor from Black Alloy, a company based in South Carolina, and it's integrated in with this blue pneumatic cylinder. Now the way this works is that once the drill bit's up to speed and it's positioned over the hole, this cylinder will actuate downward until this plunger touches off on this touch plate like so. What happens when this plunger engages is that a pneumatic stopper here will slow the feed rate of the drill as it descends, so that we can control when the drill starts to drill into the aluminum, the feed rate can slow, allowing for a clean, smooth drill. The cylinder is safety checked with a valve up top that allows it so that if we lose air suddenly to the machine, the cylinder will not crash down. Now, let's talk about the drill shuttle. The drill shuttle is designed to travel the whole length of the machine. It has a 9-foot workspace from one end of the machine to the other and is mounted on these long rail systems back here. Now, you can see in the shuttle assembly itself, we have a pneumatic cylinder. This cylinder allows the shuttle to go forward and backward to achieve drilling in the channels on the rectangular profile where there might be 2 channels. This machine can go backward and forward in order to hit those channels. We have sensors determining the position and making sure that we have achieved the channel where we want to be drilling. Motion of the shuttle is controlled via this servo back here. The servo is connected to a roller pinion which is engaged with the teeth of this roller rack from Nexen. This roller rack runs the entire length of the machine, and it is a highly machined rack that allows us to achieve a very fast speed of the shuttle. We anticipate that we should be able to hit 1.5 meters per second with the speed of this machine, which will allow for a much faster drilling rate than the machine shop is currently achieving for Koops. The machine is guarded via these light curtains, which prevent the operator from sticking their hand in or accidentally moving a piece of extrusion into the workspace during drilling. If the light curtains are broken, machine motion will stop, drilling will cease, and everything will come to a halt so that there is safety when the operators are working around it and they don't cross into the machine drilling space. Coming over here, we can see the electrical enclosures on the back of the machine. Now, we've split the enclosures into a high voltage enclosure and a low voltage enclosure. This is so that we can keep some distance between the two, mount them underneath the machine where they'll be safe from moving high-lows and other heavy equipment that often moves around the machine shop. Within the high voltage cabinet, we have our servo controls, which allow the motion of the machine across the length of the machine. We have a variable frequency drive for the drill bit. This will allow us to control the rate that the drill is spinning so we can achieve an optimal drill rate. We also have various fuses and controls for the machine, and down here is our power supply, which converts our 480 voltage into 24 voltage, which we run to the low voltage cabinet. We have power lines running across the back of the machine into the 24 voltage cabinet. Now, I apologize for the stray wires. This is still a work in progress. But in our low voltage cabinet, we have all of our safety relay systems operating for various systems. We have them for the servo, we have them for the light curtains, and we have a master control relay to make sure that the machine is getting signals from all important areas. We have all of our various relays and contactors. Down here, we have our PLC. This is a safety PLC from Allen Bradley that was given to us for this project so that we can experiment with some of the new PLC technology that Allen Bradley's been outputting lately. Here are the input and output cards, which are connected to this array of input-output terminals. This is where all the machine sensors are going to be wired directly to, and the machine systems are controlled via Ethernet. Coming over here, we can see we have our air hookup that allows us to take air from the shop, make sure that we have clean and fresh air running to all of our systems. Most of the wiring and pneumatics for this machine is done underneath the machine so that all the wires and pneumatics are tucked away out of the way of all the heavy machinery that moves around through the machine shop. That way the operators don't have the concern of tangling cables with moving extrusion pieces or any such problems that you get with trailing wires. That is the basic overview of the machine in further detail. Some of the problems that we encountered with this machine are, as you can see, it's not finished. We're hoping for deployment of this machine at the machine shop in the beginning of August. That gives us a little bit of a tight window, which was made tighter by a 2-week delay from our machining center for this overall frame. This frame was delayed about 2 weeks due to COVID, so there were a few things that we had to overcome with that. But overall, the team's been banding together very well through it. Everybody's been getting their work done on time. The design process went well. Koops has been a terrific sponsor for this project and has been very receptive to our ideas and to the overall process of designing and building this machine. This is the drilling machine for Koops Incorporated. We thank you for participating in Senior Design Project Day, and we hope that you have a good rest of your day. Thank you.